Hello. Today we're going to talk about the difference between tangential and normal components versus radial and transverse components. So when we talk about curvilinear dynamics, we can have different fields. We can have a rotating frame of reference, which is what we saw last week, where the whole frame of reference x prime y prime has an angular velocity. In that case, we use that rotating frame of reference to follow our particles, and we mentioned the example between particle A and particle B where we had a rotating frame of reference. So this is the first point. The second point is when you have a non-rotating frame of reference, but it's an inertial frame of reference, the XY Cartesian frame of reference. The second point, the second case would be when you have a particle traveling on a path and they're asking you to compute the tangential and the normal components. And this one is very useful and very easy because in this case we care about the accelerations that the particle is seeing. And remember, the particle could be very small, it could be a whole system, could be a car on a curve. And we mentioned that if, again, this is a concept that you have to remember, acceleration is a vector, meaning that you have magnitude and direction. If you change magnitude, the acceleration is non-zero. If you change direction, the magnitude is non-zero. Before, it was very simple because if the magnitude, if you did not have a change in magnitude of the acceleration, then the acceleration was zero. You didn't have to account for the direction because it was rectilinear. Now, the magnitude might be constant, but if the direction changes on a curve, the acceleration is non-zero. So keep that concept in mind. In curvilinear dynamics, even if the magnitude is conserved, but there's a change in direction, then that system is accelerating. And we mentioned the satellites being one of those cases. Okay, so that's as the second case where you have a system, a particle, a car, an airplane, where you change directions and you want to compute the normal and tangential forces on that system because you want to know what happens to the person if it's going to be too rough, the acceleration on it, and if you're going to have, if the tangential force is going to be too large, so the road is going to not be designed properly for the car to be able to stay on the road. So those type of things are considered in civil engineering and road dynamics, because if you have a road where you are going 70 miles per hour and you have a very sharp curve, then the cars are gonna fly off, right, because of the tangential acceleration. And you might hurt somebody, like a baby or your neck, if the normal force is too large. So long story short, the second case is where we care about the accelerations on a particle. That is called the tangential and normal components. That is with reference to the particle. Okay, and then it's very simple because we have that the normal component is the instantaneous velocity squared divided by the curvature rho, and that rho is given with respect to a radius of the curve. And the tangential acceleration is the change of the instantaneous velocity at that, basically is the derivative, right? Is the tangential component. Very easy. Now, the radial and transverse components are not so simple to compute because now we are again considering point of reference. So the concept is the same. In this case, the complication is that the vector ER, the vector along the radius, could vary. So now this is why people get confused. So you have two variables, the angle that changes and the radius could change. Before, when we had x and y, in a Cartesian system, rectangular system, they were always static. They were always there. You didn't have to think about x changing and y changing, because what changed was the particle's path, kind of like what we did here. But here, in the radial and transverse components, the path is there, but you're using a system, coordinate system at a point O that is not on the path. So in that case, the change, remember, ER and E theta are the unit vectors. They change in the radial component with respect to the angle is called E theta, and the change of E theta with respect to the angle is called ER. In this case, since this value is negative, you're going to have a negative ER. Okay, so the instantaneous velocity is the change of the radius in the direction of the radius. Remember, the radius can change. So you have the derivative of this is chain rule right here. We mentioned this before. This is the derivative of the radius with respect to times ER plus the radius and the change of the unit vector. Basically, this is the R Vt times ER hat, the unit vector, plus R times the change in the unit vector's magnitude or direction. Basically, it will be always the same magnitude, the direction is going to change. The unit vector is always the unit vector's magnitude, but the direction can change because of theta. All right, so if you notice, this is our velocity. Change of radius, the change of the distance r with respect to time times the unit vector, meaning that is along that line, times the distance at that instant times the change in the direction of the unit vector. That you see simplified as r dot er plus r theta dot e theta. Okay, because er dt is the same as this guy, change of theta with respect to theta. Okay, how so? Well, because we are capturing the distance, the change of the position of e theta, of the unit vector e theta, with respect to theta, but in relationship with the distance to O. Okay, so this value gives you the unit vector ER. Just look at this concept and always remember the change on the e theta unit vector with respect to theta gives you the unit vector in ER. And of course, negative as we saw in statics because we want to make sure that they're orthogonal. All right, so if you want to find the acceleration, it's even more complicated because you want to derive this guy, dv dt. So it's going to be this and that and the chain rule of that. So it's 1, 2, 3, 4. It's going to be 4 expressions that need to be derived. So r theta is going to be r theta theta er plus er theta, and they change in, and sorry, r, what I'm saying theta, I apologize, is r dot dot times er. So it's basically the derivative of this guy, rr, or r dot dot times er, right? Because the derivative of the r dot with respect to t with time is equal to r dot dot, or the second derivative of r. This is the same thing, times the unit vector er, plus the same variable is, this is r theta, r dot times er. So the er now is going to be derived. I want to do it again. So I really hope I have enough time, or enough space actually. Let's see. The r e t. If you want to derive this guy, what is that? This is the derivative of r theta. I keep saying r theta. R dot with respect to time times er plus, this is er, the derivative of ER with respect to T R dot. Okay, so this guy is R dot dot. This guy is the ER the T with ER dot plus this guy is basically the same thing, R dot, and this guy is sorry, I did something here that I need to redo because I did something wrong here. Let's do it again. Deriving it is not that easy, but using it is completely straightforward. So after this, you just have to see the equation, plug it in. Okay, so these guys are dot dot. This is stays the same, it's not derived. Okay, plus R dot, this is E dot radial. Okay, good. So that takes care of that and that. All right, perfect. So we did this part. Now that part is practically the same. So it's, let me try to do it here. The R, E, this is theta dot, only one dot, E theta, dt. Okay, so you have to do it in parts. So dr dt times theta dot theta, all right, plus r v theta dot dt e theta. Okay, cool. So this guy again is r dot, this one is theta dot dot e theta, which that is this, and then this one is plus r theta dot dot e theta. There you go, right here. Now notice that there's one last expression, which is r theta e theta, and it's because in this case we have 1, 2, and 3. Okay, so we are actually missing one more term, which is plus the dt of e theta, and this is going to be multiplied by times r theta dot. Okay, so this is the derivative, so plus r theta dot e theta dot. No, it's not very straightforward, but I just didn't have enough room. Let me see if I can get it over here. So this guy right here is the derivative of the unit vector e theta dot times r times theta dot. All right, perfect. So we already had this part right here. Now we have r theta, r dot theta dot dot, which is right here, and then r theta dot, yeah, this is, so this guy, let me see, this guy, r theta, the theta, yes, this is this, this, the r dt, yes, I apologize, I have another mistake. Actually, dr dt is r dot in theta dot, yes, so that is this one, and then the unit vector, because we have to derive that too, r theta dot e theta dot. All right, that's this guy. Oof, all right, so as you can see, it's not as easy. Even comparing can be confusing, but you just combine terms and everything that goes with ER you put together. So these two go here, and r dot theta dot dot plus, and this is r dot theta dot, all right, and theta dot dot. Okay, so if you notice, we're saying that r dot e theta is equal to r e theta dot, and that, so we have two of them. That's what we have to do right here. Okay, and the reason is because, as we said before, the unit vector is not going to change magnitude, is going to change direction. So what is captured is the change in r. That's why it's basically the same. So again, just refer to this equation. All right, and look at the book if you want to understand more about this portion. It's not extremely important at this point how to derive it. We want to know how to use it. The derivation is very clear using the changes in the path delta s. But right now, just focus on whenever they ask you for radial transversal, you have to use the velocity and the acceleration equations. So notice how different they are. The acceleration from the particle's point of view is the instant velocity plus the velocity squared divided by rho. Very simple. Versus from a inertial point of reference from a coordinate system is not so simple. But the four things that you have to know are r dot, which is the velocity in the radial and transverse direction, well, the radial direction, v theta, which is the velocity in the transversal direction, which is r delta dot, or not delta, this is theta. Okay, this is theta dot. So velocity in the transversal direction. This is velocity in the radial direction, vr. And from the acceleration point of view, we already did that part. From the radial direction is r dot dot minus r times theta dot squared, and in the transversal direction is r theta dot dot plus 2 r theta, r dot theta dot. Okay, so remember that. Okay, so this is pretty much how you take into consideration the transversal and the tangential directions. So let's look at an example. As long as you can get these four components, you're ready for any problem in this type of transversal and radial component equations. So at an instant, the length of the bar is decreased at a constant rate. So they're telling you the rate, and they're giving you units of acceleration. So this is the rate of change is r dot, and it's being lowered at a constant rate. Again, they're giving you a constant rate, so it's not accelerating, and they're giving you another speed, which is radians per second, so a rotational speed. So this is theta dot. Now, be very careful because they can give you radians per minute, they can give you revolutions per hour. So in these type of examples or problems, the only difficult part is really taking everything to radians per second. Okay, and remember, we'll have to do some examples with that. The way to transfer from revolutions to radians is with the factor 2 pi. Okay, because a whole revolution is 2 pi radians. But if they give you radians per minute, then you have to take it to radians per second. If they give you revolutions per minute, revolutions per hour, revolutions per second, take revolutions to radians per second. In short, always take your theta dot to radians per second, and your theta has to be in radians as well. So what is the velocity at point B, and what is the acceleration of point B? So they're telling you point B, so you choose your point O, which is in this case O is point A. So r is equal to 6 meters, and theta is equal to 30 degrees. But r dot, so r equals 6 meters, it's already in meters. If they give you inches, centimeters, just take it to meters. R dot is also given, which this can be measured with an accelerometer in the real world. is negative 0.2 meters per second. Now, let's see why. Because they're telling you it's being decreased. Okay? So its velocity is being, so it's a velocity value, but it's being decreased. So it's basically the direction is going down, right? It's not, it's a constant magnitude, but again, the direction is changing. So again, with the concept of changing directions is rate of change. All right, and we say that the initial angle is 30 degrees, but they're changing the transversal components. The transversal component is changing at a rate of 0.08 radians per second. All right, so we go back to using the equations that we said we needed to use. So, oh, and again, this is decreasing, so I almost made another mistake. It's negative if it's decreasing. It's very important to use the positive and negative values in these equations, otherwise you get completely different answers. So from the equations we know that the radial component's its velocity is r dot equals negative 0.2 meters per second, and the tangential component, the transverse component, is r times theta dot. Therefore this is 6 times negative 0.08 radians per second. It's given in the problem. So when you multiply that, you're going to get the transverse velocity is negative 0.48. This is meters per second. Remember that radians are not a unit of length, are a unit of rotation. So the units are meters and seconds, kind of like 2p radians. So p or 2 pi radians. And sometimes they give you rho, sometimes they give you p for a point, but the constant pi has units of radians. The units of radius will be hopefully meters. If not, you have to turn to meters. And p is the position of a particle. Okay, so in this case, the position of the interest p is at B. Okay, so just change everything they're giving you for the radius, for P particle, for radians. Don't get confused. Radians are not going to be part of your velocity. In the tangential component is meters per second. All right. So that's why when they give you radians per second, that is the speed of the particle. But when they give you the tangential or transversal velocity with respect to the point, they're expecting to see meters per second. All right, so just look at this portion right here, and email me or contact me if you have any questions. I'm basically trying to tell you, don't get confused with the radians per second. The instantaneous velocity is in meters per second. Okay, it's not meters times radians per second. You don't put the radians. It's given that the radians are part of the rotational speed. Okay, so basically to find the velocity, you just have to find your equation from the vectorial point of view. So it's negative 0.2 in the radial component minus 0.48 in the tangential component. And this is in meters per second. All right, so this is answer A. B is basically find the acceleration. So r dot dot, since it's constant, is going to be 0. So r dot dot is 0. Yep. And theta dot dot is 0. So very simple, because in this case we have r dot dot is 0 minus r is 6. So this is 0. And acceleration radially goes there. The radial acceleration is r dot dot, which in this case is 0, because it's not given as a function. It was constant, as the problem told us, minus r, which is 6, times, and the rate of angular rotation was radians per second 0.08. So this is negative 0.08 squared. So 6 times negative 0.08 squared is negative 0. But this part will be positive, but we have a negative here. So this is negative 0.038 meters per second squared. Okay, so we have one component of the vectorial acceleration. Now the transverse acceleration is r times theta dot dot plus 2 times r dot theta dot. Okay, so this is 6 times 0 plus 2 times negative 0.02 times negative 0.08. So negative and negative is positive. This is 0. I'm just looking at this answer. You can check with your calculator. Is meters per second squared. So acceleration obviously is in meters per second squared. You don't have the radians per second squared. You don't have that term. It's meters per second squared. All right, so basically you combine those two terms, and the acceleration vectorial expression is negative 0.038 plus 0.0. We're gonna have to use your calculator because this one says 0.03 and say 0.03 here. So let's use the calculator and see what's the real answer here. Calculator, and our calculator, we want to do 2 times 0.2 times 0.08. Yeah, 0.32. So that's a typo here on the book. This is an example from the book. So it's 0.032. And this is in meters per second. So this is question B. Question A was, what is the velocity at point B? And the second question is, what's the acceleration at point B? So the velocity is this vectorially, sorry, right here, negative 0.2 in radial direction plus actually negative 0.48 in transversal direction. If you actually want to find the magnitude, then you have to do square root of negative 0.2 squared plus negative 0.48 squared. That will be the magnitude of the velocity. And the acceleration, the same thing, will be the square root of negative 0.038 and 0.032 in the transversal component. But they're asking you for the vectorial expression, so this is it. So to summarize, when they ask about tangential and normal components, it's very simple. You simply have to find your instantaneous velocity, which is the change in distance with respect to time. So if they give you a function, if they tell you what is the velocity, if you have to measure it experimentally with basically with a distance divided by time, if you do average and take as you decide if this is for a engineering problem, you decide how to get your instantaneous velocity, if it's by a function or if it's by a sensor. But long story short, once you have the instantaneous velocity, then you can find your normal acceleration, which is the velocity squared divided by the radius of the curvature from the path. Tangential is extremely simple. It's just the change of the velocity with respect to time, right? So dv dt, because it's the tangential component of the path, of the velocity path. All right, so, and the acceleration obviously is dv dt plus v squared divided by rho. We did some examples already with that expression. But radial and transverse are not so simple, even though they're not complicated. You just have to use your equations correctly and follow the units. Because in this case, you have to provide your answer with respect to your point of reference. In this case, is A. For example, the example that we just did is point A, but in general, is a point O in an inertial frame of reference. So the 4 equations that you have to use are right here. Actually, there are just 2 equations, but you find the components of each expression like so. The radial component is r dot, which could be again given in the problem, or you measure with a sensor, or it could be a function. Then the transversal velocity is r times theta dot. Theta dot is in radians per second, but the velocity is in meters per second. And the acceleration is r dot dot, which if it's 0 is a great simplification. If r dot is a function, then obviously this is not a 0 value. It will have to be the derivative. And a transverse is theta dot dot, which sometimes could be 0. Sometimes you're going to have to derive your angular velocity. And this example basically shows how to compute each term and how to form your velocity and acceleration vectors.